Hi friends, this is Naneshwar Ayochar. I am having 6 years of experience in the field of simulation. I work for two of the MNC whose DCS has been used worldwide. So I decided to give the training session for those aspirants who want to make a career in the field of simulation. So usually in the refineries, different types of equipment such as heat exchangers, pumps, compressors, distillation column, and fire heaters and air coolers are used. So when we are doing the simulation for such a type of refinery plant, how to do the simulation of particular equipments, that I am going to tell you. So today I am going to take the session on simulation of heat exchanger. So let's start with types of heat exchanger. First one is shell and tube heat exchanger. Second is double pipe heat exchanger. Third one is plate type heat exchanger. So we have to first of all figure it out what is the type of heat exchanger are present in the refinery by using the PDF which we got from the customer. So generally most of the time the shell and tube heat exchanger is used in most of the refineries. So let's consider that one for simulation purpose. So second thing we need to consider while doing the simulation is the types of variables considered for the data entry of the heat exchanger. So different parameters we required during the simulation. These are the design inlet temperature of the cold fluid. Second one is design outlet temperature of the cold fluid. Third one is the design inlet temperature of the hot fluid. Then design outlet temperature of the hot fluid. Then shell side fluid flow rate and tube side fluid flow rate. The design parameters are also required while doing the simulation. The design parameters such as the type of LMTD, then in the sense is it ASE or BSE type, like that ASME type we have to first of all find it out. Then the length of the tube, then length of the shell, which will decide the total area of the heat exchanger. And if we have the details of the pitch, clearance and all the things, that also we can do the data entry for that one if it is available in the data sheet. So next one let's see the data sheet for the heat exchanger. So this type of data sheet is present when we are doing the simulation. So here you can see the number of units and surface area. So this is important for doing the simulation. When we enter the length of the tube and length of the shell, we have to check it out that this area is matching with our simulation area or not. If it is matching, then we can proceed. Then here you can see the total flow rate for the shell side. Here you can see the total flow rate for the tube side. For design purpose, here you can see the note 2. This type of instruction can be given for the design case. In the sense, this flow rate might be the operating flow rate right now. So in the note 2, they will give the instruction like if that current operating flow rate is multiple of is there any multiple factor is there for the design case. In the sense, generally the thumb rule is design flow rate equal to 1.1 time of actual flow rate or operating flow rate. So that one we need to consider. Then here you can see the operating pressure, operating temperature that we have to consider. Again, as I said previously, the operating for the design condition, when we are dealing with the design case, we have to consider the design parameter equal to 1.1 into operating parameter. So these factors, the operating temperature, inlet outlet, and for the shell side, and inlet outlet for the tube side is important. Then this pressure drop across the shell side and tube side is also important. Generally, when we are considering the design case, we have to consider this allowable pressure drop, and here this U factor is important, and while considering the simulation. So what is the significance of this U factor is, when we know the duty, from the duty we can find it out the UA parameter, like by using the formula Q is equal to LMTD. So that I will show you in the next slide. So here you can see, if this is the T1 is the temperature of the hot fluid, and if it decreasing from T1 to T2, and we are considering the cold fluid temperature is increasing from T3 to T4. So for finding out the LMTD of this type of counter flow, we are usually using this formula T1 minus T4 minus T2 minus T3 divided by ln of T1 minus T4 divided by T2 minus T3. So by calculating this LMTD, we need to put this LMTD, and we need to find it out this UA factor if it is not available in the data sheet. So these are the most important parameters we need to consider while doing the simulation. So standard procedure for doing the simulation is take a heat exchanger from the pellet, add the 4 stream, attach the streams for the inlet and outlet stream of the heat exchanger, do the data entry for the heat exchanger by using the different parameter which I mentioned in the first slide. Once the data entry has been completed, put the pressure drop spec checked during the simulation. For different type of software, different type of method is used. So I am not taking the name of the software because of the right issue. So generally while doing the simulation, when I was working in one of the company, there was a procedure that the flow pressure drop across the heat exchanger was maintained based on the K value. So here, first of all, check the pressure spec and add the mass flow rate at the inlet of the stream, add the composition for the particular stream for the shell side and tube side, put the outlet stream on a pressure specs, then start the simulation, then stop the simulation, check the mass flow rates are correct as per as the HNMB, check the temperatures for both the shell and tube heat exchangers, for both the shell and tube side are as per as the HNMB, check the duty. Once you checked and it is matched with the HNMB, change the mass spec on a pressure spec for the inlet streams of the heat exchanger, and go to the heat exchanger and change the spec from pressure spec to the K value spec while doing the simulation. Once you did all this procedure, then run the simulation once again and check the inlet outlet temperatures and flow rate as per as the requirement. If it is matching,